Thank you all for coming to our presentation. And FacePush had a demo last evening, and I hope you will all enjoy FacePush and had a good experience. And I'm Wen-Jie, and this is my colleague Hong-Yu. Both of us are from National Jiao Tong University, Taiwan. And we will be presenting FacePush, introducing normal force on face with HMDs. And this work was done in collaboration with Chia-En, Hsin-Yu, and Roshan from KO Media Design from Japan, and Liwei from NCTU. First, let us watch a short video of our work. As you can see, my colleague Chia-En is wearing FacePush and playing the boxing game. We simulate the haptic feedback of punches through the normal force on face, which is generated by FacePush. Okay. All right, so why we want to simulate forces on face, on the VR user's face? Currently, research and commercial products are trying to immerse the sense of presence in the virtual environment. Haptic becomes an important component that can enhance the immersion. Lots of prior research have explored this area, like Impacto used electrical muscle simulator as a wearable device to simulate the haptic feedback of impact and collision in VR. The other works use handheld controller to simulate haptics, like normal touch and texture touch, also the haptic links from Kai 18, and both of them simulate haptics through the handheld devices. As we can see, many works were deployed on limbs through wearable interfaces or handheld controllers. However, what about the face of the VR user? There are some different kinds of modalities of haptic feedback implemented via HMDs. Like haptic head distributes multiple vibrotactile actuators in 3 concentric ellipses around the head to provide intuitive haptic guidance. Thermal VR demonstrates embedding of 5 thermal modules on the HMD, which produce hot and cold haptic feedback, and the different locations of thermal stimuli have been used as a directional cue in exploring the virtual world. Other works focus on simulating head movements through force feedback, like Gyro VR contains a gyroscope attached to the HMD generating tangential force, which provides a feeling of inertia when conveying fast motion or an altered environment in VR. So back to our boxing scenario. We consider that through the human face, we can also enhance the sense of immersion during VR. Okay. There are still some more modalities of haptics haven't been explored on the face region. So we present FacePush and HMD integrated with a pulley system that resulting in a normal force on the user's face. There is some more related work using normal force as haptic output on wrist and body, like Squeezeback presents a use of pneumatic actuation and inflatable straps to create compression stimulus on the wrist for notification. Another work like Force Jacket, a wearable jacket attached with pneumatically actuated airbags and force sensors that provide precisely directed force and high-frequency vibration to the upper body. Combining from above, we decide to use normal force as the haptic feedback on the horizontal axis of the face via HMD. Also, we want to deploy the spatial information concept through FacePush. Now let's see how we implement FacePush. We name the device at the center as torque generating component. And this is the main component of FacePush for producing normal force. So this video demonstrates how FacePush works. Wait a second. Oh, okay. So you can see we demonstrate how FacePush works over here. And the different rotated angles produce different magnitudes of the normal force on face. For the details of the normal force generated by FacePush, we will introduce that part in the study section. Next, we define 2 states for the behavior of FacePush. The neutral state represents the torque generating component are positioned parallel to the direction of the user facing forward. At this moment, the rotate angle is 0 and there is no normal force exerted on the user's face. And the other state, if the motor are rotated, we define this situation as push state. It represents the torque generating component is rotated and translates a belt pull into a HMD push. At this moment, we can assign the angle to generate different magnitude of normal force during push state. So this figure shows each component of FacePush. The DC motor works as the power source of FacePush, and we use rotary encoder to record the position of motor, so we can assign the angle where the DC motor should rotate. And as we connect the motor shaft and the belt of the HMD by a coupling and the 3D printed clip-on hinge, then attach the torque generating component on both sides. The video. Okay. This video shows how torque generating component is assembled, and the 4 parts are, you can see, and after the assemble, we just use a clip-on hinge to attach to the both sides of the HMD. Okay. After that, we define 2 ways to use the push generated by FacePush in our applications. The first type, we name it discrete stimulus. The discrete stimulus is an impulse representing a short duration of contact, and it increases and decreases instantly in 0.5 seconds. And the other one, we name it continuous stimuli. The duration of continuous stimuli covers the whole application, but the intensity is different among users. And we use these stimulus depends on the scenario of our applications. So now we will show 3 different applications of FacePush. The first one is, I'm sorry. The first one is the boxing demo last night. So we use the discrete stimulus in the boxing game. FacePush exerts corresponding pressure depends on the different types of punch. And in the diving, the next one is, sorry. The second one is about diving example. And in this example, we try to simulate the water current acting on your face when user is swimming. So we utilize the continuous stimuli of FacePush, and its strength will be adjusted according to how fast and slow the user swims. Okay. And the final one is about the The final one is about the attention guidance. And we use continuous stimuli as a directional cue in watching a 360 video. And users sometimes miss the important content when watching a 360 video. So we use FacePush to remind the user where to look at during their watching. Okay. And now we will introduce the user studies and our results of FacePush in the rest of the presentation.
Thanks, Wen-Jie. In this work, we carry out 2 user studies. In the first user study, we find enjoyable forces for FacePush. In study 1, we conducted 3 minor studies. We defined the appropriate pressure based on the results from studies above. Before we move on to our user studies, we want to find the mapping between rotated angle and the pressure acting on face. Therefore, we placed 5 pressure sensors on the face module as shown in the figure. We obtain a linear equation of the average pressure and the rotated angles as shown in the figure. The result represents a single pressure sensor. We use a pressure unit which is proportional to the actual force exerted on the user's face. The total force can be approximated by multiplying the pressure by the contact area of the facial interface of the HMD. After we confirm the relationship between angle and the pressure, next we conducted an ADT study to know the least pressure needed to be felt by users. We conducted a standard 2 down 1 up staircase study and take the average of last 5 trials to be threshold estimation. The threshold is 2.694 kPa, which indicates FacePush must generate at least greater than it, such that participants begin to feel the pressure on their face. Next, we use discrimination threshold to find distance between forces to be discernible. We use 4 base pressures and offset pressures. We define 75% of users to be able to distinguish between 2 stimuli as ZND. According to our results, we find the base pressure 2.575 and 2.7 need a delta pressure 0.5 so that the user can distinguish. They are also the best pressure for comfort experiment. Finally, we evaluate the subjective rating of comfort and where the pressure comes from. We choose 6 pressures from ZND and use 6 Latin words to decide order for every participant. The experiment is a repeated measures design. Participants measure comfort with 7-point Likert scale. The left picture is about comfort. The right one is the percentage of force coming from face. It shows when the pressure increases, the subjective comfort is reduced, and the pressure comes from the head surround. Finally, we decide to use 2.7 kPa as our criterion for pressure. We are also interested in whether FacePush enhances user engagement in virtual reality boxing experiences. So we conduct study 2. Each participant walks through 4 levels and must evaluate the level realism and the enjoyment in boxing game. Afterward, an open-ended interview to get general comments about the system. The result is shown in the figure. The result shows FacePush enhances the enjoyment and realism in our VR boxing game. Most of the feedback are positive. Our participants feel engaged with FacePush. Some participants state that sometimes feel not well when FacePushing is pushing. We believe these results are due to the distance from the eyes to the HMD during pushing is reduced, causing the focus to change temporarily. It may bring out nausea and blurred vision. However, the participant didn't report it clearly. We consider the future research can address these discomforts by automating the focus adjustment. The delimitation of FacePush is about weight and noise. The weight gained by the motors sometimes cause the HMD slide down a little bit. While the motor is rotating, it generates some noise. These limitations are due to that we are using motors. However, this can overcome by using different mechanisms, such as embedding shape memory alloys into the belt. About the future work, we would like to achieve the following 2 points. First, apply FacePush to other parts of the body, for example, wrist or finger. Second, combine FacePush with other simulated facial feedback, such as thermal. For example, when user experiences the diving game, he can feel the temperature of water flow. Finally, we summarize FacePush into 3 contributions. We propose a pulley system, FacePush, to render the haptic sensations through pressure acting on user's face. Also, we conduct studies to determine which pressure is best generated. Third, we use 3 applications to show discrete and continuous normal force. Thank you for your attention, and we are happy to take any questions.
Questions? Oh, that was not a question? Okay. All right. Very cool stuff. I like actuations in the face for different reasons, but I'm actually wondering, given that this is a very sensitive area, if you got any of the participants to comment on not discomfort necessarily, but surprise or something, because it is something that we don't really expect, and we're very sort of adjusted to.
So actually we did some comfort studies to make sure the pressure we generated to the face is appropriate for the users. So is that you want to ask about?
I was just wondering if people had more comments on the effect and the sensations in the face, because some people are more sensitive to them, especially around the eyes, right? That's a very sensitive region.
More sensitive.
The second question I have on this is that by moving the device around, you're also creating a visual effect, if you think about it, right? Yes, you might lose focus, which is a downside, but on the other hand, you're creating sort of a distortion for a brief amount of time. Is that something that you maybe can play around with?
Play around, you mean?
You're basically actuating the headset, right?
Yeah.
So you're creating a visual sensation by temporarily blurring the image or something.
And actually, we think this can be adjusted by another mechanism. So maybe we don't use. It's not very significantly affect the sense of what you see in the VR. So basically, it's
I think it could be a feature.
Yeah,
like
feature.
You should think about that. Okay, Jotaro.
Okay, I'm Jotaro from HPI. That was really exciting work. Thank you for your talk. I can imagine while you're using HMD, you can feel you can also feel the push sensation, but also you can feel the lateral force on the belt, right? On the HMD belt, if you pull it on using the motors. I can imagine you can also render such another side effect of by using those motors. And also, I'm also really curious to see with this device you could also induce a different illusion effect rather than push. Is it possible to do illusion, face pull with this device?
Face pull. Basically, but HMD, you can only tighten up the belt and to create a push effect. But the pull effect is on the other direction. So we haven't solved about it yet. But for present, we try to combine different type of the feedbacks like thermal and the pressure. So so we can create more haptic feedbacks in the VR. Yeah.
Thanks so much.
Okay, and before you guys all leave, don't forget to spend those best talk tickets on your way out. So I want to thank all the speakers and you guys again.